Hello and welcome back. Today's class will talk about calculus of variations, which is a fundamental topic which is necessary to understand partial differential equations based techniques for image segmentation. Okay, so this is the calculus of variations is what gives rise to many of those techniques. We will have a brief look at this method just to understand where it comes from and the fundamental Euler-Lagrange equations. So we will look at the historical origin of the calculus of variation. So in the early 1600s, John Bernoulli, one of the mathematicians in Europe, renowned mathematician in Europe, at that time posed the so-called Brachistochrone problem. So the problem statement is given below. I'll just read that out. So given points A and B in a vertical plane, to find the path A, M, B, down which a movable point M must, by virtue of its weight, proceed from A to B in the shortest possible time. So basically, it's a point mass of mass M, small m, and it's going to travel in the vertical plane. We look at the images next slide. From A to B, starting point is A, ending point is B, and you have to find the idea is to find the path of that particle or bead. You think of it as a bead on a string. So find the path of that particle or a point. And it's of course it's moving by virtue of its weight. It means that the only external force is the gravitational force, right? It's acting downwards. And the idea is to optimize for the time. So you have to find out the shortest possible time, the path which gives you the shortest possible time. So this is like an optimization problem, except that the solution is not just one number or a coordinate, but rather an entire path or a curve or a function, right? So we will look at the details of this problem in the next few slides. So here is the slightly more detailed overview of the problem. So you consider the particle m of mass m. So the small m is the mass. Poor notation. Sorry about that. But the gravitational field of strength g. So this is the acceleration due to gravity, right? G, and it moves along the curve. The curve is parameterized by x. So y is a curve. Y of x is the equation of the curve between 2 points A and B. And of course, it's in a vertical plane. And the time of descent of the particle is given by ds over v. So the ds over v is basically if the particle travels along the curved path by an infinitesimal length ds, called the arc length, then the time it takes is given by ds over v, where v is the speed of the point mass or the particle. Okay, and ds is the length along the curve. So it takes a curved path. For the general path is the curved path. So if it travels a distance ds along that curved path, then the time taken by it will be ds over v, where v is its speed, right? L is the length of the curve and v is the speed of the particle. And you can also denote the total time taken if you think of it as t, right? That will be the total, capital T will be the total time taken. So this is the problem statement. So we are trying to optimize for time. So we have to find the path that gives the shortest time. So if you have looked at optimization problems before, for instance, in neural networks, we are looking for parameters that provide the smallest loss function, right? In a lot of cases in optimization, you have some form of cost function, and you usually try to estimate parameters in that optimization problem so that the cost function or loss function is small. Here the loss function, if you want to think of it, is the time taken. Time taken should be just as minimum as it can get. And what parameter are we trying to estimate here? We are not trying to determine a parameter, rather we are trying to determine an entire curve or a function. Okay? So these are the kind of problems that is concerned in the field of that you are concerned with in the field of calculus of variations. Okay, so we'll get a slightly more detailed look, because I haven't shown you any pictures so far, just talking about these things. Okay, so without any loss of generality, we can say, okay, that this is the vertical plane, right? You can think of this as the y-axis, and this is maybe x. Okay, so and you're trying to get from A to B, right, in the shortest possible time. So what is the path then? What is the curve that will take you from path or curve that will take you from A to B, and this m here, this is the point mass you're talking about. G is the acceleration due to gravity. So so we are trying to estimate this equation of this part, right? And we call this y of x. Now, how do you go about doing this? So if you look at it intuitively, then you would immediately say, let's choose the shortest path. The shortest path is the straight line between A and B. That's what is given here. This is the straight line. So if you look at it, this is the straight line, right? So ideally, you would think of the shortest path, straight line path would give you the least time. But also think about the other way. If you let the particle drop a bit vertically, quite a bit, then it will gain speed. Right, because it's motion under gravity, it will gain speed. So you are not giving it any extra momentum, you're just dropping it. So it will gain speed, and so then if you think about it, in which case the time is still can be reduced because you have higher speed. But the problem with this approach is when you let it drop so that it gains speed, is that you have a longer path. Right? So if you want to increase its speed or velocity, you need to traverse a slightly longer path, but it will be very high speed. So then you have a good chance of reaching there quickly from A to B quickly. On the other hand, if you are just choosing the shortest length, then maybe velocity is not that great, and typically is like that, right? And so then you might not get. Then even though the time might be reduced because the path is shorter, they're still not very clear, right? So there is two things at tension here, right? Longer path, high speed; shorter path, low speed, right? So we don't know which is better. Now you have to find a compromise between these two. So in many of the problems we will talk about, segmentation problems we will talk about, this kind of tension will be there between two different quantities that we are trying to minimize, right? So and those situations is where calculus of variation comes in handy. So it provides you a systematic way to arrive at correct solutions. Okay, so in this case, what we are trying to figure out is the equation of this curve. So mathematically, the problem is formulated as follows. So we want to minimize the total time taken, which is what this integral gives you, right? Okay. And we saw that dt can be written as ds over v, and that in turn can be written as 1 over v square root of 1 plus y prime squared. So what is y prime? Y prime is nothing but y prime is dy by dx. I'll just write it out here. This is a very common derivation. You can actually Google this and you'll find it everywhere. Wikipedia pages for it. So I'm not going to go into detail, but eventually you have to do a few substitutions basically for the velocity also, because the v you can get by conservation of energy, right? So if ya is the maybe I'll have to zoom in a bit. So ya is the position of the starting point, right? So this is the coordinate of the starting point ya. If it drops a distance y, then it gains some kinetic energy. Okay, so your initial energy is purely potential. So using conservation of energy, you can evaluate an expression for v from this equation above, right? And then substitute back in the integral. So that will give you this integral, the integral expression for the time, a definite integral expression for the time, which is 1 over square root 2g and integral a to b and whatever is in these brackets. Of course, this on the numerator, this is y prime squared. Okay, just keep that in mind. Maybe I'll zoom in a little bit just to make sure that usually tilts. So yeah, so you can y prime squared. So this is the integral that we want to optimize, right? So we want to find the minimum time. Okay, so this integral is what is referred to as the functional. Okay, so this is the functional. So functional takes as input a function, in this case a curve, and returns a scalar value. So in this case, it's the total time taken, and we want to minimize the functional to arrive at an optimum path, which is basically y. We want to figure out y of x. That's what we need. All right. So we'll revisit this once you finish the derivation. Okay. If you want to minimize time, which is basically this is the functional, then you have to find a path y. So it's an entire function. So okay. So the general goal here is to maximize or minimize definite integrals of this form. So if you note, it's a definite integral a to b, and f here with the integrand is a function of y prime, which is dy by dx, and x. Okay, this j of y itself is referred to as a functional. Okay. So like I had said it earlier, a function takes an argument. For instance, if it's a 1D function defined on the real line, let's say, takes as x an input on the real line and returns a value which is typically another scalar on the real line. Right? Typically a scalar, while a functional in this case takes as input a function. The input to this functional is y. Y is a function. It's a curve, but it's still a function, and returns a scalar value. Okay. So when you optimize functions, right, what it does, it provides the location of the optimum. So let's say f of x is x squared. Let's say you're optimizing something like x squared, right? The location of the optimum is x star equal to 0. Right? That's where the function f of x takes its lowest value. Okay. So in this case, when you optimize this functional, what you're trying to do is to estimate y, the function itself. Right? So you want to estimate a function which will optimize this function. It's the idea. Okay. Now there are some other aspects, like this is actually defined in infinite dimensional space, because if you look at this typical function optimization, let's say 1D, f of x equal to x square. Now x is just in one dimension, right? But when you're trying to estimate an entire function, then the problem is defined in infinite dimensional space. Here again, the infinite dimensionality comes from how you represent the function, in what basis you represent the function. So for instance, if you use a Fourier basis, or you're using Fourier series or Fourier transform, there are infinite number of terms. So consequently, you are in an infinite dimensional space, making the problem a lot harder. Okay, so just to reiterate, so let's consider this picture here, and I'll try to tell you what we are trying to explain here. So let's assume that the solution to the problem we studied, right? So let's solution here. Let's just this x, this y. Solution we wanted. So the solution curve, which is basically the curve that we want to estimate from A to B. So I put A here and B there. Okay. So my B is slightly out of that off. Sorry. Let me just put B properly. Okay. So B here, and let's say the black curve is the correct solution, right? It's the curve that gives you the shortest time of travel from A to B. So that's the black curve. I have to use a color that I haven't used here, so I just stick with black. So black curve is the correct solution, right? That's the one right here. That's correct. Okay. So we all know that when you work with minimization of functions, etc. Let's say we have some. We are now talking about a different topic. So let's say we have this function f of x, right? Okay. And this is defined on the real line. So x is from minus infinity to infinity. Take on all values on the real line, and f of x is a scalar valued function. The output is also a scalar. Okay, so it returns a scalar. So let's say x star is the point at which f of x attains a minimum. I will just talk about minimum, right? So x star is the x star is the x at which f of x becomes minimum. So if you look at any perturbation around x star, so if you look at, let's say, x star minus delta x, and also you can do f of x star plus delta x. Small perturbations. Maybe I have to rewrite x star a bit. It just looks messy. Okay. So if you look at this, then you see that for all these values, when you move to the left a bit or to the right a bit, since x star is the minimum, but there are other assumptions here. I'm assuming that there's only one minimum for f of x, right? A global minima, and there are no local minima, etc. We have to make all the necessary assumptions, right? But then still we are only looking at the neighborhood of a minimum, right? So x star minus delta x and x star plus delta x. If you move either to the left or the right, then f of x in that case, for all, if you f of x star minus delta x and as well as f of x star plus delta x, and everything in between except for x star will be greater or than the value at f of x star. So all value of f of x will be greater than strict or equal to f of let me just write this down. F of x star. Right? So this is true. Right? If your x star is the minimum, gives you the minimum value of f of x, and it's at x star, then if you perturb the value of x around x star, then all values of f of x will be higher than that, right? Will be greater than that. So it's very simple. If you let's say if you draw, let me wipe this out and draw, so it's easier, right? Very simple function like this parabolic function, right? So if this is your minimum right there, if you move to the right or to the left, the function value increases. That's what I'm trying to say. Okay. So similarly, but then this is in the real axis. Of course, you can also consider it in multiple dimensions, x, y, z, or x1, x2 up to xn. But the argument remains the same. If you perturb it a little bit around where it attains its optimum value, in this case its minimum value, the x values, the coordinate values, then the function value will increase. Right. So how do you do similar perturbations in when you're trying to estimate function? So if this is our correct optimal function, right? If this black curve is our y hat of x, this is the path that gives you the shortest time in our problem we are studying. But in general, for any such definite integral we saw, let's say this is the function that gives you the least value of the functional. Then how do we perturb this? So you perturb this by adding a test function, h of x, right? That's how you do. Here you added delta x, you are adding h of x. And it should of course satisfy the boundary conditions here, because boundary conditions is that, it's in our case, the particle or the point mass starts at A and ends up at B. Okay. So the boundary condition it should satisfy, so which means that h of A equal to h of B equal to 0. So that at the ends of the path, your boundary conditions are met. And this is true for any other problem. There will always be a boundary condition and you have to meet them. This is one way to meet it. So h of x think of h of x as a small perturbation to y hat of x, which is the correct curve that we are seeking. Okay. This is how we perturb it, right? Because it's like you said, it's an infinite basis or infinite dimensional space. The only way you can perturb y of x is by adding another test function to it, right? So this is, of course, this is the important point that you have to understand in the calculus of variations. And how do you perturb this function, right? And we are not done yet, so we'll also look at what further calculations are required in order to arrive at the so-called Euler-Lagrange equation. Okay. So we seek I call it the extremum of j of y. So we just but you have to pass this in your mind, saying we seek to find some y such that j of y attains a minimum value. Or you can also say maximum value, but you can always change the sign and do that. Okay, and there are boundary conditions to be met, such that y of a equal to y subscript a, and y of b equal to y subscript. These are typically given, so you understand that. And the integrand is some function which is a function of x, y of x, and y prime of x. Sometimes you can also have higher derivatives, so y double prime of x. We'll see that this actually happens in some of the image processing problems. So we'll see about that when we get there. Okay. So we seek the extremum of j of y. That's what I call it, extremum. Once again, this optimization literature has different definition, etc. So I'm just being very informal. So don't hold me to this a little bit. Okay. So I assume that we're just trying to find out y such that j of y is minimum. This functional is minimum. Right. That's the idea. So, like we said, we have to perturb it around the optimal solution, right? So, which is basically, we assume that y hat is that function for which j of y attains minimum value. So, we then try to perturb it. That's what we do, right? This is again a familiar trick. You remember when you also try to take derivatives, then we do something like that, right? So, we have a infinitesimal change in the arguments, and then we try to see how the function changes. Right. So similarly, that's what we are trying to do here, except that we have to parameterize carefully. So we saw that we are trying to, in the previous slide, we tried to do y hat plus h. Right. That's much harder to do actually. Right. Because what do we eventually want? We want to estimate this. Right. We want to estimate. right? So that's what you would do if you want to find out the maximum or minimum of, let's say, an arbitrary function. I'm using f here all the while, but you feel to put something g, or if you want h also. So if you would ideally do df by dx and set it to 0. This will give you a maxima or minima, and you would look at the sign of the second derivative, and you will also examine the sign of d square f by dx square, and that will give you whether it's a maximum or a minimum. But in either case, this is the first step. You have to set this to 0, right? And the way you would do that now, if you want to start on first principle, then you will perturb f of x. You have to write as f of x plus delta x, etc. So we want to write dj by dy, and this is hard to compute using just this this kind of trick, right? But then we have to perturb everything by h and then h prime, and then you have to say h is small. So because when you do f, right, this kind of derivative you will do by f of x plus delta x minus f of x, right? Something of this sort. I don't want to write too much around here, just to give an idea. So you will do f of x plus delta x minus f of x and divide by delta x. That's how we estimate the first derivative, correct? So this is in the limit of delta x tends to 0, that gives you df by dx. Right? So that's the idea. So but then to do that here, you have to do some, you reparameterize so that it's a lot easier to do. So what you do is, instead of h, you write y of x plus epsilon eta of x. So that's what we have here, this term. So it's epsilon, write it back here, epsilon eta of x. So eta of x can be any function. Of course, we assume that it's typically well behaved, that it doesn't have some nasty discontinuities, but generally eta is any function, eta of x is any function. And epsilon is a very small number, right? The delta is a very small increment that you add on it. So this way you can perturb around y hat, right? You can perturb around y hat and see how this changes. So now j is now strictly a function of epsilon. Why is that? Because y hat is fixed. We now assume that y hat is the correct curve that we are seeking, and the curve for which j of y is minimum, or j of y hat is the smallest value j of y can take. And we perturb it with epsilon eta. We fix eta also. We say it's a test function. It can be any function. Without loss of generality, we can say it can be any function eta. And which, of course, like I said, has desirable, well-behaved function. We don't want some pathological function, right? Something that goes into infinity and all that. We don't take. We just say, it's a function which is well-behaved, does derivatives, first and second derivatives exist, right? And then we can just use that to perturb. So now that's also fixed. So the only thing that we are changing is epsilon. So we are actually searching in the neighborhood of y hat, just making sure that for any such value of epsilon, your function takes j, the functional takes higher values than at j of y hat. Okay. So then we've calculated what is known as the first variation. So that, and before we do that, define what the total variation is. Total variation is given by this expression. Delta j is j of epsilon minus j of 0. So what is j of 0? Just put epsilon equals 0 with just the functional which is estimated at y hat, right? And y hat of x and y hat prime of x, right? So now we can write the total variation in this form, j of epsilon minus j of 0. I have just substituted for j of epsilon here and j of 0 here. Now the second step is, of course, bring them under the same make them one integrand under the same integral. And if you look at this, you can just then now you do your usual tricks, like you can do a Taylor series expansion of f of x, y hat of x plus epsilon eta, y hat prime of x plus epsilon eta prime. So you can think of f of x as a function of several variables, and you do a Taylor series expansion. So, and then once you do that, you will see that this term will cancel out, and what is remained is what we will refer to as the you can call it the first variation. The left hand side also, the total variation can also be expanded as a Taylor series, and once again the j of 0 will then get subtracted out, because that's what we are expanding around, right? Around j of 0. And once we do that, then we get this term which is known as the first variation. Okay, first variation, which is nothing but dj by d epsilon at evaluated at epsilon equal to 0, and it will turn out that it's this expression on the right. Right, and in order for for the minimum to occur at y hat, it turns out that delta j should be 0. Okay, it's not too hard to see, because you see the delta j expression for delta j is an odd function of epsilon. Okay. So if you change the sign of epsilon, okay, then then what happens is automatically changes the sign here at delta j. See, delta j is j epsilon minus j of 0. See, this is the minimum, right? J of 0 is the minimum. Okay. Any other perturbation should only increase the value of j. So, but if I change the sign of epsilon, okay, you can show that this will become a positive number, and this change the sign of epsilon will change the sign of your of the value of delta j. So that means that you can get higher or lower values. So that's not correct. So then you have to set delta j equal to 0. So we can show that delta j equal to 0. That's again like a theorem you can prove. And once you set that to 0, then the next step happens. So a necessary condition for the functional j of y to have a relative minimum or maximum at y equal to y hat is that the first variation vanish. Okay. So this is like a theorem. I'm not going to prove it, but I just gave you like a kind of hand waving argument, because delta of j, which is called the first variation, is an odd function of epsilon. Okay. So by changing the sign of epsilon, we can make it lower than j of 0, which is not true, right? Because j of 0 corresponds to y hat, and that is we know that when we have assumed that way we defined it is that it is the value at the correct or the optimal solution of y. So then by changing the sign of epsilon, we can make the total variation positive or negative. So to prevent that, the only way that can be prevented is by making delta j equal to 0. Okay. So the theorem once again is, for the necessary condition for the functional to have a relative minimum or maximum at y equal to y hat is that the first variation of j of y vanish. That is, that delta j equal to 0 for y equal to y hat and for all admissible variations eta of x. So once this is done, then we can go here and look at what happens if we set this to 0. Okay. Again, it's other way of looking at it is that you are setting the first derivative to 0. Okay. That's an easier way to look at it. Set that to 0, right? And once you set that to 0, one other thing that we have to do is we have to simplify this expression. So this f of y prime, once again, sorry if I have not mentioned this earlier, f of y f subscript y is nothing but delta f by delta y, and f subscript y prime is delta f by delta y. Okay. So we assume that. So we can do integration by parts. So if we take the second expression, we can do integration by parts and use the boundary condition to eventually come at this expression. Okay. Now all you have to do is focus on the term in the brackets. Okay. Now it turns out that we can prove, in order for the integral to be 0, right, for any eta x, this term should go to 0. The term that I have put in red bracket should go to 0. Okay, that's another thing. See that we did integration by part for this f of y prime, derivative with respect to y prime. Okay, and if you have y integrate, we'll have a derivative with respect to y double prime. If f is a function of y double prime also, then we'll have another term. We'll have to do integration by parts twice, right? That we can prove. Okay. So the coefficient of eta of x, I'm sorry, there's an error here. Coefficient of eta of x should vanish for all choices of eta satisfying boundary conditions leading to the Euler-Lagrange equation. So these are the Euler-Lagrange equations for any choice of eta of x. Okay. So now these equations are partial differential equations. Okay, and this is what you use to actually estimate y. Okay, see that it is a function of both y and y prime, and in this case, because we started out with f strictly as a function of x, y and y prime. Okay, sometimes it is also a function of y double prime, which is d square y by dx square, and in which case there will be an additional term with a change in sign. Okay, so we'll look at that in another slide, but that's one of the things that you have to remember. It can also be a function of higher derivatives, and for that, and what happens is that when you want to solve that, if you go back to the previous, and so there will be one more term here. We'll look at that later. Okay, and that's why here, like I was talking about, if j of y and where f is a function of y double prime also here, then you will end up with an equation like this. Of course, the sign will be flipped. Note that the sign is flipped. That's because you will do integration by parts twice, and there will be a minus sign, extra minus sign, which will make this positive. Okay, so this is the Euler-Lagrange equation, and this is what is the driver for all the methods that rely on uh, all the PDE based methods and that rely on calculus of variations. Okay. So we will look at something called snakes active contours. That's one of the earliest techniques that was derived using the Euler-Lagrange equations. And then subsequently other techniques also came about, and they used something called another technique called level sets to make computations simpler and more efficient. So we'll look at that in the subsequent videos. Okay, so that we will stop here for now.